In text mining, most of the time we are dealing with a lot of text documents from surveys, feedbacks, logs, articles, blogs and so on. And the goal of text mining is to find out the essence of information or topics in these documents. A corpus refers to the set of documents we used for text mining. There are 7 practice areas in text mining. A text mining process makes use of technologies from many fields of study. A practice area refers a field of study where some of its application or techniques are used in the text mining process. The 7 areas practices commonly used in text mining are: 1. Informational retrieval. 2. Document classification. 3. Information extraction. 4. Document clustering. 5. Web mining. 6. Natural language processing. 7. Concept extraction. Let's take a look at a Venn diagram in next slide. A Venn diagram of the intersection of text mining and 6 related fields, shown as ovals, such as data mining, statistics, and computational linguistics. The 7 text mining practice areas exist at the major intersections of text mining with its 6 related fields.
Information retrieval. Information retrieval is the study of searching and retrieving a subset of documents from a universe of document collections in response to a search query. The documents are often unstructured in nature and contain vast amounts of textual data. The documents retrieved should be relevant to the information needs of the user who performed the search query. Several applications of information retrieval has evolved over the past decade. Search engines such as Google, Bing, and Yahoo facilitating this process use a variety of advanced methods. An information retrieval system's efficiency lies in its ability to match a user's query with the most relevant documents in a corpus. To make the information retrieval process more efficient, documents are required to be organized, indexed, and tagged with metadata based on the original content of the documents. Figure 1 shows a generic information retrieval system architecture.
Hi, my name is Matt Cutts. I'm an engineer in the quality group at Google, and I'd like to talk today about what happens when you do a web search. The first thing to understand is that when you do a Google search, you aren't actually searching the web. You're searching Google's index of the web, or at least as much of it as we can find. We do this with software programs called spiders. Spiders start by fetching a few web pages. Then they follow the links on those pages and fetch the pages they point to, and follow all the links on those pages and fetch the pages they link to, and so on until we've indexed a pretty big chunk of the web. Many billions of pages stored across thousands of machines. Now, suppose I want to know how fast a cheetah can run. I type in my search, say cheetah running speed, and hit return. Our software searches our index to find every page that includes those search terms. In this case, there are hundreds of thousands of possible results. How does Google decide which few documents I really want? By asking questions, more than 200 of them, like, how many times does this page contain your keywords? Do the words appear in the title? In the URL? Directly adjacent? Does the page include synonyms for those words? Is this page from a quality website, or is it low quality, even spammy? What is this page's page rank? That's a formula invented by our founders Larry Page and Sergey Brin that rates a web page's importance by looking at how many outside links point to it and how important those links are. Finally, we combine all those factors together to produce each page's overall score and send you back your search results about half a second after you submit your search. At Google, we take our commitment to delivering useful and impartial search results very seriously. We don't ever accept payment to add a site to our index, update it more often, or improve its ranking. Let's take a look at my search results. Each entry includes a title, a URL, and a snippet of text to help me decide whether this page is what I'm looking for. I also see links to similar pages, Google's most recent stored version of that page, and related searches that I might want to try next. And sometimes, along the right and at the top, I'll see ads. We take our advertising business very seriously as well, both our commitment to deliver the best possible audience for advertisers and to strive to only show ads that you really want to see. We're very careful to distinguish your ads from regular search results. And we won't show you any ads at all if we can't find any that we think will help you find the information you're looking for. Which in this case, the cheetah's top running speed is more than 60 miles an hour. Thanks for watching. I hope this made Google a little bit more understandable.
Information retrieval example on Google Search. Google Search uses web crawlers. Example, Googlebot or Spider to discover publicly available web pages. Crawlers look at web pages and follow links on those pages. They go from link to link and bring data about those web pages back to Google's servers. The software pays special attention to new sites, changes to existing sites and dead links. Computer programs determine which sites to crawl, how often, and how many pages to fetch from each site. Pages crawled are used to create an index, so we know exactly how to look things up. Much like the index in the back of a book, the Google index includes information about words and their locations.
For inquiry, Google algorithms rely on more than 200 clues to guess what a user is trying to look for. Examples of clues include certain key terms on the web pages, your region, and page rank. What is page rank? Page rank is a numeric value that represents how important a page is on the web. Google figures that when one page links to another page, it is effectively casting a vote for the other page. The more votes that are cast for a page, the more important the page must be. Also, the importance of the page that is casting the vote determines how important the vote itself is. Google calculates a page's importance from the votes cast for it. How important each vote is taken into account when a page's page rank is calculated.
Hi, I am Googlebot. I send out requests for web pages across the internet, download the pages and then pass them off to the Google Index server. I find pages two ways. By crawling the web like a spider and by inviting people to submit their URL to Google. Sorts all the pages gathered from Googlebot similar to a book index. Tells the doc server which pages contain the words that match the query. Query is retrieved from the doc server. Snippets are created to describe each search result. Result pages are ranked based on their query relevance. Google uses a complex algorithm to determine page rank. Google Web Server sends the query to the index server.
Document classification is the process of finding commonalities in the documents in a corpus and grouping them into predetermined labels. Supervised learning, based on the topical themes exhibited by the documents. Task is to assign a document to one or more classes or categories based on some rules, example, classification rules. Supervised learning technique uses predetermined labels or categories. Some of the common applications of document classification are email forwarding and spam detection, call center routing and news articles. A document can be in more than one classification. Example: a document about benefits of eating durian can be classified under health and fruits category. Information extraction: unstructured data, like text documents, can contain small fragments of information that might be of specific interest, based on the context of information and the purpose of analysis. Information extraction is the process of extracting these fragments of data, such as the names of people, organizations, places, addresses, dates, times, and so on, from documents.
Hi, in this segment I'm going to introduce the two tasks of named entity recognition and information extraction, methods for getting simple structured information out of text documents. Let's start with information extraction. The goal of information extraction systems is to find and understand limited relevant parts of a text. And normally we're going to run it in a context where the system gathers information across many pieces of text. And the goal of doing this information gathering is to be able to produce some sort of structured representation of the relevant information. So you can think of it as instances of a database relation, so rows in a database table, or as a knowledge base. And when we do information extraction, we can have one of two goals. One goal is to directly help people to organize information so that it's useful to people. And the other possibility is to put the information in semantically precise form. So commonly, computers for other downstream information processing tasks won't be able to perform them if the input is just natural language text. But if we can have pulled out various kinds of relations, such as a database table, then it's very easy to do subsequent data mining and processing. So the kind of information that IE systems extract is clear factual information, the kind of who did what to whom, when kind of information. So let's take a look at an example of that. So here are a couple of examples. One's gathering earnings, profits, board members, headquarters, any of this kind of factual information about companies from company reports. So the idea is that the system can look through the text and then it sees, okay, here's the name of a company, and then it's talking about its headquarters, and it says that the headquarters are located in, so that's kind of an indicator of a headquarters location, Melbourne, Australia. And what we're going to get out of that then is this relation, which you can think of as an instance of a database table. That's only one example. There are lots of other examples. Another example is this one that I show here. There are lots of cases in biotext mining, so learning drug gene product interactions, learning subcellular localizations, lots of relations of interest to bioscientists in various ways have been worked on in information extraction systems. In the more consumer space, information extraction is now available and I think popular in various applications like either Apple or Google Mail, or is used in web indexing. So here's a little example from Apple Mail, and so here there's this date, and so Apple Mail recognized that there was a date there and put in that little arrow box. And when I hold that down, it's then offering to create a calendar event for me. And so that's kind of a little help of allowing me to do that kind of task faster. This kind of information extraction is often fairly simple and seems to be mainly based on using the kind of regular expressions that we saw earlier, including name lists. Here's one more example about how companies are starting to surface information extraction and search applications. So if I stick into Google BHP Bulletin headquarters, as well as regular web search results, there's actually giving me right here, best guess for headquarters is Melbourne, London. Now, of course, we can argue a little about whether that's the perfect answer. They're really kind of two separate answers here. BHP Bulletin's actually kind of a complex case because they have this complicated dual company structure, and there is a Melbourne office and a London office. So we'll call that, just about correct. Okay, that was information extraction. Let me now go on and look at a particular subtask that has become very important, named entity recognition. So the idea of named entity recognition is that we're going to, in particular, just look for and classify names in a text. So the first step is we find names. So here we've then found a name, and in particular what that means is we're finding the limits of the name. So this one is these 2 tokens, this name is this 1 token, and then once we've done that, we're going to classify the names. So we're going to say that this name here is a person name, this here is the name of an organization, this is a date, and then we have a sequence of further person names. So I guess this one's Rob Oakeshott and goes across the line break. So to say a little bit more precisely what the task is, we have this sort of phrase of named entity recognition, and it's a little bit of a code word these days that reflects the history. The idea of it was that entities were meant to refer to discrete things in the world. So I am an entity, Stanford University is an entity, but something like sand or air isn't an entity, that there's not a specific delineated physical thing. And then the idea of named were that some entities have names. So I, Christopher Manning, have a name, but the chair I am sitting in as I record this, it is also an entity. It's a discrete physical thing, but it doesn't actually have a name attached to it, so it's not a named entity. That's the kind of philosophical history. In practice, as the word is used in named entity recognition, that's not quite what it means, because effectively what we're doing is using named entity recognition to mean easily distinguishable names or other things in text that we can pick out. So in particular, 2010, so things like dates, times, quantities are normally regarded as named entities, although according to the original starting point of the name, something like a date or a chemical or a protein isn't actually an entity at all, but we always include those kinds of things when we're building named entity recognition systems. Okay, so what is the use of named entity recognition systems? Well, named entities, if you identify them in a text, they're something that can be indexed or linked off. So as I note down below, many companies make use of various techniques for tagging entities on web pages, and then they can provide links off of those entities to bio pages or topic pages or other things of that sort. So there are a whole bunch of commercial products that run as web services that allow you to do that kind of thing. If in general you want to be crawling the web and picking up sentiment, we discussed earlier detecting sentiment as to whether it's positive or negative, but you will then also need to work out who the sentiment is about or what the sentiment is about. And so at that point you need to be picking out the company or product names in the text, and that's a task of named entity recognition. But there are a lot of other uses where named entity recognition is a subcomponent of a larger task. And so commonly, when you're doing information extraction, a lot of what you're doing is actually identifying named entities and then working out the relationship between them. So we'll talk later about question answering. And in question answering, for various kinds of questions, often the answers are named entities. When did something happen or who did something? And so it helps a lot for question answering if you have good named entity extraction. Another example that we also saw of how people use named entity recognition that plays off this having semantically interpreted information is to use it in then various kinds of things like calendaring applications where you're making use of the semantic interpretation. Okay, I hope that's enough to have given you guys a good sense of these two tasks. Named entity recognition of simply picking out concrete names of objects, people, organizations, etc., or quantities, dates, times, and things like that. And then the bigger task of information extraction, where the goal is to pick out particular relations, rows in a database table from pieces of unstructured natural language text.
Information extraction example. Information extraction example. Document clustering. Clustering partitions objects, example, like terms of words, in a data set into groups so that the objects within a group, cluster, are similar and the objects between the groups are dissimilar. Help users understand the natural grouping in a data set. It is an unsupervised learning technique, that means there is no predefined labels or categories. Document clustering uses algorithms from data mining to group similar documents into clusters based on predefined degree of similarity, example, co-citation count.
What is web mining? Web mining is the use of data mining techniques to discover and extract information from World Wide Web, WWW, or Internet. Web is a collection of interrelated files on one or more web servers. Web data includes web content, text, image, records. Web structure, hyperlinks, tags. Web usage, HTTP logs, app server logs. Examples of information extracted from web data. User behaviors pattern analysis, example which hospital's website in Singapore is most frequently visited and which location. Link analysis. Example, on a web page, which the most frequently clicked links.
Web mining. Taxonomy. Study the flow chart. Web mining. Taxonomy. Study the flow chart. The 4V of web data: volume, velocity, variety, veracity. As the internet becomes even more ingrained in our popular culture with the rise of Facebook, Twitter, and other social media channels, web mining will continue to increase in value. What is natural language processing, NLP? Natural language processing, NLP, is the ability of a computer program to understand human speech as it is spoken or text as it is written. Human language is very complex for a computer to understand. Read the following two sentences. Mary had a little lamb and drove her car to a farm. At the farm she sold it to Old MacDonald. We know that it is most likely referring to the lamb. However, this process is very complicated for a computer to figure out who or what is it.
This lecture is about the natural language content analysis. Natural language content analysis is the foundation of text mining. So we're going to first talk about this. And in particular, natural language processing would affect how we can represent text data. And this determines what algorithms can be used to analyze and mine text data. We're going to take a look at the basic concepts in natural language first. And I'm going to explain these concepts using a simple example that you are seeing here. A dog is chasing a boy on the playground. Now, this is a very simple sentence. When we read such a sentence, we don't have to think about it to get the meaning of it. But when a computer has to understand the sentence, the computer has to go through several steps. First, the computer needs to know what are the words, how to segment the words. In English, this is very easy, and we can just look at the space. And then the computer would need to know the categories of these words, syntactic categories. So for example, dog is a noun, chasing is a verb, boy is another noun, etc. And this is called a lexical analysis. In particular, tagging these words with these syntactic categories is called a part of speech tagging. After that, the computer also needs to figure out the relation between these words. So a and the dog would form a noun phrase. On the playground would be a prepositional phrase, etc. And there is a certain way for them to be connected together in order to generate the meaning. Some other combinations may not make sense. And this is called syntactic parsing, or syntactic analysis, or parsing of a natural language sentence. The outcome is a parse tree that you are seeing here. That tells us the structure of the sentence so that we know how we can interpret the sentence. But this is not semantics yet. So in order to get the meaning, we would have to map these phrases and these structures into some real-world entities that we have in our mind. So dog is a concept that we know, and a boy is a concept that we know. So connecting these phrases with what we know is understanding. Now for a computer, would have to formally represent these entities by using symbols. So dog D1 means D1 is a dog. Boy B1 means B1 refers to a boy, etc. And we also represented the chasing action as a predicate. So chasing is a predicate here with three arguments, D1, B1, and P1, which is a playground. Right? So this is a formal representation of the semantics of this sentence. Once we reach that level of understanding, we might also make inferences. For example, if we assume there's a rule that says if someone is being chased, then the person can get scared, then we can infer this boy might be scared. This is the inferred meaning based on our additional knowledge. And finally, we might even further infer what this sentence is requesting, or why the person who said the sentence is saying this sentence. And so this has to do with understanding the purpose of saying this sentence. And this is called speech act analysis or pragmatic analysis, which refers to the use of language. So in this case, a person saying this might be reminding another person to bring back the dog. Right? So this means when saying a sentence, the person actually takes the action. So the action here is to make a request. Now, this slide clearly shows that in order to really understand a sentence, there are a lot of things that the computer has to do. Now, in general, it's very hard for the computer to do everything, especially if we want it to do everything correctly. Now, this is still very difficult. Now, the main reason why natural language processing is very difficult is because it's designed to make human communications efficient. As a result, for example, we omit a lot of common sense knowledge because we assume all of us have this knowledge. There's no need to encode this knowledge, and that makes communication efficient. We also keep a lot of ambiguities, like ambiguities of words. And this is again because we assume we have the ability to disambiguate a word. So there's no problem with having the same word to mean possibly different things in different contexts. Yet for a computer, this would be very difficult because the computer does not have the common sense knowledge that we do. So the computer would be confused indeed. And this makes it hard for natural language processing. Indeed, it makes it very hard for every step in the slide that I showed you earlier. Ambiguity is a main killer, meaning that in every step there are multiple choices and the computer would have to decide what's the right choice, and that decision can be very difficult, as you will see also in a moment. And in general, we need common sense reasoning in order to fully understand the natural language. And computers today don't yet have that. And that's why it's very hard for computers to precisely understand the natural language at this point. So here are some specific examples of challenges. Think about the word level ambiguity. A word like design can be a noun or a verb. So we've got the ambiguous part of speech tag. Root has also multiple meanings. It can be of mathematical sense, like in square root, or it can be the root of a plant. Syntactic ambiguity refers to different interpretations of a sentence in terms of structures. So for example, natural language processing can actually be interpreted in two ways. Right? So one is the ordinary meaning that we will be getting as we are talking about this topic. So it's processing of natural language. But there is also another possible interpretation, which is to say language processing is natural. Now, we don't generally have this problem, but imagine if we want the computer to determine the structure, the computer would actually have to make a choice between the two. Another classic example is a man saw a boy with a telescope. This ambiguity lies in the question, who had the telescope? This is called a prepositional phrase attachment ambiguity, meaning where to attach this prepositional phrase with the telescope. Should it modify the boy, or should it be modifying saw, the verb? Another problem is anaphora resolution. John persuaded Bill to buy a TV for himself. Does himself refer to John or Bill? Presupposition is another difficulty. He has quit smoking implies that he smoked before, and we need to have such knowledge in order to understand the languages. Because of these problems, the state-of-the-art natural language processing techniques cannot do anything perfectly. Even for the simplest part of speech tagging, we still cannot solve the whole problem. The accuracy that I listed here, which is about 97%, was just taken from some studies earlier. And these studies obviously have to be using particular data sets. So the numbers here are not really meaningful if you take it out of the context of the data set that are used for evaluation. But I show these numbers mainly to give you some sense about the accuracy or how well we can do things like this. It doesn't mean on any data set the accuracy will be precisely 97%. But in general, we can do part of speech tagging fairly well, although not perfectly. Parsing would be more difficult, but for partial parsing, meaning to get, let's say, some phrases correct, we can probably achieve 90% or better accuracy. But to get the complete parse tree correctly is still very, very difficult. For semantic analysis, we can also do some aspects of semantic analysis, particularly extraction of entities and relations. So, for example, recognizing this is a person, that's a location, and this person and that person met in some place, etc. We can also do word sense disambiguation to some extent. We can figure out the occurrence of root in this sentence refers to the mathematical sense, etc. Sentiment analysis is another aspect of semantic analysis that we can do. That means we can tag the sentence as generally positive when it's talking about the product or talking about the person. Inference, however, is very hard, and we generally cannot do that for any big domain, and it's only feasible for very limited domain. And that's a generally difficult problem in artificial intelligence. Speech act analysis is also very difficult, and we can only do this probably for very specialized cases with a lot of help from human to annotate enough data for the computers to learn from. So the slide also shows that computers are far from being able to understand natural language precisely. And that also explains why the text mining problem is difficult, because we cannot rely on mechanical approaches or computational methods to understand the language precisely. Therefore, we have to use whatever we have today, particularly statistical machine learning methods or statistical analysis methods, to try to get as much meaning out from the text as possible. And later you will see that there are actually many such algorithms that can indeed extract interesting knowledge from text, even though we cannot really fully understand the meaning of all the natural language sentences precisely.
Three major aspects of natural language processing which are important for effective understanding of text content by human or computer. 1. Syntax. The syntax describes the form of the language, like the grammar. 2. Semantics. The semantics is a study of meaning and interpretation of words, sentences in a language. 3. Pragmatics. Explains how the sentence relates to the world. That is, it has to take into account the context of the sentence, the state of the world, the goals of the speaker and the listener. Applications of NLP include sentimental analysis, document classification, email filtering. What is concept extraction? Concept extraction is the technique of mining the most important topic or concept of a document. Sometimes also known as concept mining. Extracting concepts from text, quite similar to information extraction. Analogy. When you read a long text, we will normally search for the key concepts or themes in the text. In the e-commerce context, concept extraction can be used to identify what a shopping-related web pages is talking about. Concept extraction. The diagram shows a text mining environment. The diagram shows an overview text analytics process. The diagram shows an overview text analytics process. Data collection. Relevant raw data are collected based on the business objectives. Example. A Polytechnic wants to help more students to graduate from their 3-year diploma. This can be done by early intervention on underachieved students. Raw data, relevant, to be collected and analyzed could be students' grades of past students over 5 cohorts. Students' subject grades, final and class assessment. Students' financial status. Other students working part-time. What students' raw data is not relevant or useful. Text parsing. Extraction of words from the corpus and cleanse. Example, white spaces, symbols like HTML, unknown symbols hash. Determine parts of speech, pose, for each word using NLP example. Determine the word is an adjective, noun, verb. Stemming of words. Example run, run is normalized to run. Remove words with little information. Example the, you, run. Normalize words of same meaning, synonyms. Example vehicle and car normalize to car. Text filtering. After parsing, there are still words, or terms, which may still be irrelevant to either for differentiating documents from each other or for summarizing the documents. Hence, further reduction of terms needed and customization of terms based on a specific business domain may be needed. This is often one of the most time-consuming and subjective tasks in all of the text mining steps. It requires a fair amount of subject matter knowledge, or domain expertise. Example: if the corpus of documents are related to diseases, medical experts may be sought. Text transformation. In this phase, there will be further reduction of words and creation of the matrix, called term by document matrix or TBDM, containing keywords and their weights that can represent the guy's information and concepts of the corpus of text documents under analysis. This matrix is then ready for analysis during the different data mining techniques. Text mining. In this activity, different data mining techniques like clustering, concept or topic extraction can be used, depending on the business objectives. Note that the text mining process is iterative. Example: if there are additional similar documents added to the existing corpus or new expert opinion is consulted, the process need to be repeated.
Survey analysis using SAS text analytics. This presentation will feature a project in which 15,000 free-form survey responses from an online print company were analyzed. SAS Text Miner was used for discovery and to uncover areas of importance for sentiment analysis. SAS Sentiment Analysis was used to assess the tonality of those areas. SAS Enterprise Content Categorization was used to analyze root cause and understand factors driving positive or negative sentiment. SAS Enterprise Business Intelligence was used to surface end-user reports and display the results of the analysis. The process begins in SAS Text Miner. This is the interactive filter viewer. It displays the raw survey responses at the top and a frequency list of terms below. In examining this list, it becomes possible to see some of the key things the survey respondents are talking about. Words like order, quality, service, shipping. These are all words that are used frequently in the survey responses and would likely be a good idea to assess sentiment on. There are also a few markers for sentiment in this list as well. Good, great, love. However, we aren't seeing these words in context, so people might be saying not good, not great, or don't love. Viewing the concept links on good, we can see what good is associated with. Good deal, good quality, good value. Overall, those seem fairly positive and might set the stage for our sentiment analysis. Overall, it seems like the word good is used in a positive context, so we might expect to see more positive sentiment than negative. We can put what we've learned in using TextMiner to work in SAS sentiment analysis. In this analysis, we will assess sentiment on two areas or products: overall, which features the business facets we uncovered using text mining, and products, which were derived using the structured data associated with the survey. SAS sentiment analysis gives users the power to analyze sentiment at a truly granular feature level. Using a combination of statistical and linguistic techniques, it becomes possible to assess what a customer is saying. Testing empowers users to iterate through their documents, identify areas for improvement, and refine their results, all using color coding. In this survey response, there are matches for 3 feature rules: prices with a negative on could not have afforded, and both offers and orders trigger on discount. The results of the analysis can be surfaced through SAS business intelligence tools. We can start by looking at the overall sentiment results. Overall isn't always very helpful because of the neutral bucket. Neutral can be true neutral, for example, I have no comment. It could also be a situation where you have a positive and negative cancel each other out. For example, customer service is amazing, but the print is blurry. You have a positive hit for amazing, a negative hit for blurry. They cancel out and become neutral. Drilling into our feature level sentiment is much more meaningful. As noted earlier in TextMiner, the majority of the sentiment in this project is rather positive, except for the sentiment around the print. Print has 76% negative sentiment. This is worthy of further exploration because printing is what this company does. From here, we can drill into the detailed survey responses and see if we can identify anecdotally what's driving the sentiment. We see things like poor screen printing. Print on my cards is very small. Printing on shirts was a little blurry. Just by reading, it can be difficult to quantify the problem. Further analysis is in order to find out what is really driving that negative sentiment. It's worth going back into TextMiner and exploring. Back in TextMiner, we can explore print as a noun. In the concept links, print as a noun is associated with light, small, large, read. If we drill a little bit further, we can see what read might be associated with. And under read, we see things like barely, difficult, hard. It looks like size is often an issue, as is the fact that people are having a difficulty or hard time reading the print. These concepts can be used to develop a small taxonomy so we can further quantify the problems. Here are the concepts in SAS Enterprise Content Categorization. The problem areas, blurry, small, large, contain simple classifiers and a rule that looks for those classifiers in sentences with the rules defining print. For example, the print is too small. The font was blurry. Scoring the survey responses against the taxonomy gives us data. A simple frequency analysis can be run to show us where the largest concentrations lie. In this case, the overwhelming majority of hits come from the rules for small. We can drill further to see how small is being used in context. This shows that many people are complaining about the print or fonts being too small on the products they receive. This is one of the driving factors behind the high concentration of negative sentiment for print. The process outlined during this presentation can be applied to many unstructured data initiatives, not just survey analysis. These tools are highly flexible and empower analysts to uncover valuable insights from their unstructured data.
SAS Text Miner Tool. SAS Text Miner Tool. We have come to the end of the lesson. Now attempt to the quiz and gauge how much you have learned.